Any questions or anything? Yes, no questions as of now. Right. Yeah, what we'll be doing, we'll be continuing from where we left off, right? Okay. So let me recollect very few things so that we get connected to the things which we have discussed till now. But like I had a sessions on starting with a question, trying to answer a question. Okay, let me share my screen. Okay, wait a minute. Yes, I guess you can see the screen. Right. So we started with asking a question, why do we study quantum statistical physics? Why to study statistical study, or you can take it as why one should understand statistical physics to go and do well in the case of quantum computing and in case of quantum technology and anything in this direction. Okay, we did answer this question mainly because all the quantum hardware, okay, right, depends on or made up of okay, very tiny particles, very tiny, okay, which are quantum particles, by the way, right? And these particles dynamics and its dynamics, okay, dictated by quantum physics, right? So within the quantum physics, this branch of statistical mechanics is there. It is actually quantum mechanics. So within the quantum mechanics, the statistical physics there, a branch of physics, which allows us to understand if the particles are treated in a different manner, okay, and how are they going to interact with each other. That is, we are going to understand and design our quantum computing or quantum hardware with a knowledge on that. Okay. So in today's session, we'll continue from there on. Okay. Just to recollect, we did talk about the probability of particles to exist in a particular state and all those things. And if I take a collection of particles, they can be arranged in different energy states in the groups. So the way the probability distribution of the particles to exist in these groups is decided by, okay, further we discussed Gibbs probability distribution, okay, distribution, or you can also call it as Gibbs principle or Gibbs energy and so on. Those are the things we have discussed so far. Okay, right? Now, in today's today's session, what we are going to talk about is the way we treat the particles, okay, or the way we perceive the particles. If we perceive in a particular manner, what they would dynamically behave, okay, right? So there are ways the perception is actually dictated by the nature of the particles, okay. So what I mean is, so today's session, okay, in today's session we would be discussing on, okay, the nature of the particles, okay, dictating the perception of the particles, okay. The nature, their nature itself dictates us to describe them in a particular manner and perceive them further and do some kind of a computing with them. Okay, so that is what we are going to do today. So what we'll do, we'll always start with our old method. The old method is the method which we are comfortable with, the method which we are like known to see in real world. Okay, so that method is called classical level or classical real world. Okay, right? So in a classical real world, okay, there are systems around, particles around. Okay, so let me start with, I am talking about particles around us, and in that, let's say I have identical particles around me, identical particles. Okay, fine. So we are starting with identical particles. How many number of identical particles I am talking about? Let's say I consider n identical particle. Let's say these particles are confined in a volume of V. Confined in a volume of V. Okay. Now it is considered the usually in real world scenario. How are we going to describe them? We are going to describe them description. Okay. How are we going to description is give the description is we'll describe them with the moment position operator. Let's say particle in position q1, q2, and qn. Position operators. You can say position operators, position vectors. Okay. And we also in real life specify if the particle is moving, we specify with the momentum. Okay. And linear momentum. Linear momentum means particle is having some mass moving with the velocity v, mass into velocity is a linear momentum. Okay. Now I want to make things slightly complicated, means more complex. What we'll do, let me go at slightly smaller level, like smaller level in the sense, if the particles are rotating about a nucleus, okay, right, I'm going straight away into the quantum level. Let's say if the particle is rotating about the nucleus, okay, so it has some linear momentum, okay, p, and it is about some radius. So r cross p would give you what? Angular momentum. So because of the angular momentum, what happens is a particle is electron revolving about the nucleus. It is going to have a orbital spin moment. Okay. So now let me talk about these particles are of that kind. So there is a orbital spin moment ms1, ms2, and so on, msn. Please remember, I started with a classical any particle represented by position momentum, but there is not fun there for me. So what I'll do, I'll go a little bit further, smaller and smaller. Now, okay, identical particles along with the position momentum also represented with the spin coordinates. Very good. Okay, now the particles are quantum in nature, which means I have to represent them in terms of wave function. So the particles are at the quantum level. So what do I do? I'll straight away bringing in quantum description. Okay, the quantum description for me is wave function. What is the wave function is? A quantum wave function psi would depend upon the moment position operator q1, q2 up to qn, momentum operator p1, p2, up to Pn. Okay. And next, orbital spin operator ms1, ms2 up to msn. Okay. Here you see ms spin is up spin or a down spin because it is decided by the angular momentum. If something is rotating in a circular fashion, you can give your fingers curling for the orbital motion, and take your thumb, which is going to give you angular momentum, that is going to give you a spin orbital angular momentum. So this is a quantum state representation or a quantum description of this identical particles. Okay. So this is a mathematical description. Now comes the actual fun. What is the actual fun is, in a classical scenario, right? Let's time being forget about there being electrons. So let's see things from the classical perspective. Okay. So seeing things through classical perception. Okay. So it is named as Maxwell-Boltzmann statistics. Okay. You will understand that what is this statistics once we go through the details. Okay. In a classical scenario, very important. Okay. Particles are strictly considered to be distinguishable. It's obvious, right? Okay. Because things are no more fuzzy. Specifically, I can see something is placed classically in a particular location clearly, because it is not going to move here and there, because it doesn't have that probabilistic nature in a classical world, in a real world. So what we do, as per the classical perception, you can straight away say the particles are, even the identical particles are distinguishable. Means I can say where they are located and how they are. Okay, even though like particles, let's say there are two colored balls are kept on the table. I'll say there is a ball on the left side located, the ball on the right side located. Okay. Now one more thing is, as per this classical perception, okay, any number of particles could be right placed or housed in single particle state in a same, I think I'll say same particle state. Okay, what I mean is, there is no restriction. Once I keep one particle on some location, some place, there is no restriction that I should not put one more particle there. I can always keep particle. There is nothing like in a given, like on a table, I can put as many number of colored balls or something, some entities. Okay. So my classical perception gives identical, even the identical particles are distinguishable. Any number of particles could be placed in a same particle state. Okay. I will call it the same particle state sum S. Right. Now, when okay, with this, some fun begins. What is the fun? Now, let's say I change the particle's position. Okay. If I change the particle position, let's say there is a left colored ball and there is a right ball, another red colored ball in some location. If I interchange their location, okay, what I see while interchanging, you might notice, I'm just interchanging. You would straight away say, this, after interchanging, the arrangement of the balls is changed, because the earlier, even though color is same, but altogether it's a different ball, indistinguishable. Let's say you can think in terms of, there is a very small red color ball, very large blue color, red color ball. The color is same, the size is different because they are distinguishable. Now, if I interchange them, I'm creating a new state overall. Okay, right? So here, even though I'm talking in terms of quantum in nature, let's say this kind of a scenario exists where particles are distinguishable. If they're interchanging, sorry, any number of particles could be in the same state. Then if they're interchanged, if I get a new state, okay, if I get a new state, what happens? I will have, okay, I'll have I will have a new state which is being formed. So that new state is, I can simply write in terms of quantum state representation as there is a quantum state psi Q1, or let's say particles with the classical perception is represented with some wave function Q1, Q2, Q3 up to, let's say, for example, Q4, I'll just take up to Qn. So this is a quantum state. This is a quantum state. Now, I have formed a new quantum state by just interchanging, let's say, particle 2 and particle 3. Okay. Okay. So this time I'll represent a new state is formed as psi prime. Please see these two quantum states. I will not say quantum state. These two states are not same. They are two different states. Two different states obtained or created by just interchanging the two particles. Okay. Remember, this is not correct as per the quantum mechanics. In the quantum mechanics case, we see something else. But in real world scenario, this is what happens. So this is as per the Max Boltzmann statistics. We'll come to what is the inference, what are the implications of this Boltzmann statistics. We'll see. For the time being, we are seeing things, even the particles, identical particles, from the perception of quantum particle, from the perception of classical eye. Okay, to the classical eye I'm seeing. Now let me go further. Now, what happens in the quantum scenario? Okay, now let me start quantum, okay, scenario. So in the quantum scenario, see, straight away particles must be indistinguishable, intrinsically indistinguishable. So they are so tiny, I can't distinguish them. Okay, so number one statement is, even though identical particles, even you can start with identical particles, okay, identical particles must be intrinsically, by default, indistinguishable, not indistinguishable. You can't distinguish them. Okay, indistinguishable. Okay, that is one thing straight away as per the quantum mechanics, right? And one more thing is, while counting the possible accessible states for a set of n particles, okay, right? Okay, no new states would be generated when I interchange the two particles, because then the moment indistinguishable, I don't know whether the particular particle placed here or there. Okay. The next implication with the indistinguishability is interchanging the particles, whether it is a location or linear momentum or spin momentum or anything, interchanging the particles, let's say two of them, is not going to generate new state. Is not going to generate a new state. Okay, that is for sure. Okay, now what matters for us is how many number of particles are there in such a given state. Okay, right? So the question is how many number of particles I can place? How many number of particles I can place or I can house in a given single state? Yes. Okay. Any number of particles are there. Sorry, the particles are there. One thing is they're indistinguishable. Another thing is by interchanging them, they are not going to create a new quantum state or a generate new quantum state. Okay. So if that are the things given, how many number of particles I can place? So what kind of particles I am talking about? Let's say electrons revolving, creating spin moment, spin up or spin down. Okay, right? Doesn't matter where they're located, a particular orbit or somewhere outside the system, electron sides of the atom or all those things. Okay, so if that is the case, now how should I answer this particular question? How many number of particles I can place? Okay, so just now I took electrons. There are some other particles are also called photons, right? So in this case, I should know how to place the particles in a particular state or how they exist. Depending on the existence, you should be able to recognize what kind of a particles are these. Okay, right? So interestingly for us, there is a help coming from something called symmetry requirement. Okay, right? So you can borrow information from something called symmetry requirements to answer the question what I posed earlier. Symmetry requirements. What is the symmetry requirement says? It's a fundamental quantum mechanical postulate. Okay, as per quantum mechanics. Okay, what it says is, okay, if there are spin particles, okay, for a spin particle, right? If there are two kinds I can have, the spin of a particle is integer spin particle, integer, or even say people call integral or integer. Integer in the sense the spin of a particle is represented with the integer numbers. Another one is half integer spin particles. Half integer spin particles. Okay. So here the spin of the particle is, let's say, 1, 2, 3, and so on. And here the spin is half, 3 by 2, 5 by 2, and so on. Okay. Where? So here overall number of particle is n. Sorry. Here n by 2. N is an odd number. You can say NO, odd number. And the above you can have any number. Even or odd, doesn't matter. So if the particles having a spin of such a thing, okay, now there is some implications due to the spin, whatever value they have. Okay, for example, if you take an integer spin particles, what is going to happen is, okay, right? So example, integer spin particle examples. Just now I gave a photons. Okay, remember photons do have integer spins, and helium 4 atoms, they have integer spin. Okay, right? So these spin particles, okay, when they measure, their spin is going to be in terms of unit in the units of Planck's constant, possess spin moment measured in terms of or in units of h, Planck's constant units. Now the values are starting from even 0, 1, 2 up to n. Even 0, if system doesn't have any spin, its equals at 0. Okay. Now integer spin particles if you have. Now what is happening is, let's say I interchange any two particles here. Okay, right? So as per the quantum mechanics, right? Okay, by interchanging the identical particle, okay, which are indistinguishable, let's say I interchange by coordinate of any two particles. If I have this integer spin particles, you know what is happens? The quantum state which is going to be generated by interchanging any of the two coordinate system, I'm not going to get a new state. I'm getting the old state, but the new state is simply represented in terms of the interchanged coordinates. Okay, what I mean is, let's say a given coordinate system for me right now, I have a Q1, P1, and MS1. These are the three dimensions or 3 degrees of freedom I have. Let me convert this all the three into or represent all of them with a simple Qi or Q1. So here I am writing as a Q, small q1, p1, ms1, right? So let me represent the q1. Okay. So now, if I have integer spin particles, let's say quantum state is represented by q1, q2, okay, qi, qj, qn. Okay. Now what I will do, I'll just interchange both of them. I'll get a new quantum state q1, q2, qj, qi, qn. Interestingly, what is the new quantum state which is formed is same as the old system. Okay. So this is called symmetric wave function. Okay. Symmetric. Even though I interchange the coordinates of two of them, so the particles satisfy the symmetric wave function. So these particles are called bosons. So this kind of particles were identified, put together in one group by boson, okay, sorry, Bose and Shin together, and they gave us some statistical behavior in terms of statistical distribution. To understand them, you have to understand a statistical distribution based on this simple two implications: indistinguishability. Interchanging would not create a new quantum state. So these are actually called the particles satisfying this kind of a behavior, satisfying or showing such behavior are called bosons, and they are known for showing or they obey Bose-Einstein statistics. Okay. So the best remembering, for example, best ones are photons. Photons are the bosons. Now keep this aside. Now let's think in terms of half integral spin particles. Okay. Now I want to understand. Let's say I have a particles whose spin is half integer. Half integer spin particles. Okay. Examples, I can straight away give you examples. Okay. Examples are electrons and helium-3. Earlier helium-4. Now it is helium-3. Okay. So the spin is again here. The spin of the system of these particles is going to have value half. half, 3 by 2, 5 by 2, and so on, n by 2, where n is an odd number. Okay, and measured in terms of Planck's constant units. As usual, spin is measured in terms of Planck's constant units. Now, interestingly, if you take these particles, okay, and if we interchange their location, okay, right, what happens? Particles on interchanging their, let's say, positions I'll interchange some particular coordinate system. The coordinates I interchange. By interchanging their coordinates would generate a new quantum state. Remember, but there exists a relation between the new quantum state to old quantum state in such a way it is just a new quantum state is equivalent to a negative value of the old quantum state. Okay, right? What I mean is, let's say I have a quantum system state where Q1, Q2, Qi, Qj, Qn. So n particles are there. Now what I do, I interchange the positions of two particles, means I'm picking one particle, another particle, just interchanging. Just put them into two different locations. Okay? What is happening is, it is going to generate a quantum state 1, Q1, Q2, Qj, Qi, Qn, but the new state is simply equal to minus of the old state. Okay, so which means the new state which is formed negative of the old state, this is similar to the previous case, only differed by a minus sign. So these quantum states are called antisymmetric. So these quantum states are called antisymmetric. They have symmetry, but negative sign is there. Symmetric are the symmetric states. Okay. Now there is a implication due to this antisymmetry. Okay, what is the right? Okay, what is the implication is, okay, let's say I have two particles. Okay, let's say now the implication of, okay, implication of antisymmetry. Now consider two particles. Okay, two particles, by the way, these are indistinguishable. Okay, right, indistinguishable, and these two particles are considered if they able to locate in same state, means same coordinates, if they are able to exist in the same coordinate space. Okay, right, which means I'll have quantum state which is Q1, Q2, Qi, Qj, Qn. Right? I and j is any some indices. Now, two particles are both existing with the same Qi. Okay? Right? So here, both particles are existing with the same coordinates. Okay, what coordinates I am taking? Qi. Okay, both are represented by same coordinates. Like on a three-dimensional surface space, in same location, two particles are there. Let's say, okay. In that case, no, they are on the same location. Okay, so by interchanging things, it's not possible, by the way, to interchange on same location. Let's say somehow their nature got interchanged, the spin got interchanged. Okay, right? By interchanging their spin. Okay, here I think spin is also said. By interchanging the system, what happens? As per our previous case, if I interchange the particles, what was the scenario? Okay, the scenario is it is going to generate. Okay, it is going to generate a quantum state negative of that value, the old quantum state. But as per now, the thing which I took, the quantum states are, okay, quantum states are, by the way, if two particles are in same location, interchanging doesn't affect anything because they're in the same location. So the condition here I have is the quantum state, the old one, let's say in a Q form, Qi, the two particles are there. On the same Qi, I interchanged. I got, okay, I got no effect. Okay, but the implication earlier is by implication earlier is as per the earlier, if you interchange the particles, you have to get a negative sign. So it's a contradictory. It is contradicting. So the contradictory effect implies that there is no chance two particles are indistinguishable with integer spins can be in one location. Okay, and so this contradicts the concept of interchanging particles generate antisymmetry. Okay, so you can simply say, therefore, no two particles of half integer spin could be in one location, could be in one state. Okay, so that is straightforward. Given, by the way, it is also supported by what? Pauli's exclusion principle. Pauli's exclusion principle. Okay, he told that in a given orbit, I can't have same spin electrons in a given orbit. So either I can have up spin and a down spin in that same orbit. So I can just put same number of pairs depending on S orbit or a P orbit or a D orbit or a F orbit. Okay, so please remember, integer spin particles are, when I separate, relocate them, that is going to generate antisymmetric quantum state. And more than this, the important factor is I can't place integer spin particle, half integer spin particle in a same location by putting them together. Okay, so the particles which shows this behavior are called fermions. Particles of this type are called fermions. Fermion. Okay, and they show and they obey Fermi-Dirac statistics. Fermi-Dirac statistics. Okay, we wanted to know what is this Bose-Einstein statistics and Fermi-Dirac statistics. Okay, and more than that, we want to study the quantum qubits realized out of electrons in a given atom, giving us chance to realize a qubit, and photons giving a chance for us to realize qubits by putting them inside a cavity, and their polarization is going to give me to allow one to realize a qubit. Okay, right? So I hope everybody gets that. Okay, so basically, to summarize till now, okay, right, there are two types of particles I have for qubits. The one is electrons as qubits. Another one is photons as a qubits. Okay, we want to realize both are all useful for quantum computing. They have electrons have, okay, half integer spin. They say 1 by 2, 3 by 2, and so on spins. And these guys have 0, 1, 2, 3, okay, integer spins. And these guys show, they show Fermi-Dirac statistics. Fermi-Dirac statistics. What is this statistics? Anti-symmetry wave function. Anti-symmetric wave. And these guys show Bose-Einstein statistics. Statistics. And they are about to show, actually not about to symmetric wave functions. Okay, their wave functions are symmetric by nature, means interchanging them is not going to generate any new quantum state. Okay, yes, in the case of electrons, there is a new quantum state is generated, but that quantum states are only differed by parity, the sign, the negative sign. So I can represent psi going from minus psi with interchange. Psi remain to be psi even after interchange. Interchange states. Okay, so that is what so far the Bose-Einstein and Fermi-Dirac statistics. We'll go a little bit in depth and try to understand what insights we could get through them. Okay, right? So quickly, let me see if there is any questions. No questions. Okay, so now we have another friend of us, that is Boltzmann statistics, that is a real world statistics. We'll keep that also in the perspective and see all the three guys in one go, so that we will remember what are, like, where are we at, what are we dealing with. Okay, understanding, let me do that, understanding, okay, statistics of the particles. Statistics, by the way, dynamics are the existence of the particles. Statistics means existence of the particles, okay, with various perception. Okay, if you want, you can write with various perception. Remember, the perception is not independent of this particles type, because when you are looking at the electrons, you can't look at in a different way that you can say they are going to have integer spins. Not possible. They are always going to have half integer spins. So you have to look from their perspective and perceive them from their perspective. Okay. Now, to understand the statistics of particles from the way, all the possible scenario, let's consider two particles. Example, I'm just taking, consider two particles. Okay, I've considered, let me name them A and B. Easier for me. The moment I say two particles A and B, you should recollect that we are starting with the real world scenario where the particles are distinguishable. Okay, now two particles are considered. I'm naming them as A and B. Okay, let's say there are three states available for these particles, and there are three states available. Okay, three states available. What I mean, let's say each state is represented by a label S. S is taking 1, 2, 3. Okay. S stands for, S is equal to 1 stands for state 1. S 2 stands for state 2. S is equal to 3 stands for state 3. Okay. Now, I wanted to divide and see the perception into 3 ways. Let me divide into 3 ways. First one is Maxwell-Boltzmann statistics, MBS. Okay. And the second one is Fermi-Dirac statistics. The third one is Bose-Einstein's statistics. Okay. Right. So Max-Boltzmann, Fermi-Dirac, and Bose-Einstein. Okay, first, what is the real world scenario? Max-Boltzmann scenario is distinguishability. Distinguishable. Fine. Any number of particles can be in any state. Any number in any state. Okay, fine. If that is the scenario, let me write down what are the various possible scenarios for each case. Okay, now I'll have a small table once again within that. Okay, small table. Okay, for example, yes, a particle can be in any state, okay, any number, and they are distinguishable by the way. So let's say I want to talk about how many number of states are, like which state I'm talking about. S is equal to 1, S is equal to 2, S is equal to 3. I have 2 particles. I can have both the particles in same state, A, B. Both the particles A and B in state 1, another situation. Both the particles in state 2. Okay, another situation. Both the particles in state 3. Okay, right? So, very good. Fine. Okay, so now another possibility. Let's say one particle is in state 1, another particle is in state 2. That is also possible. Okay, so A and B. By the way, the distinguishable means interchanging doesn't make any difference. Okay, so that does make a difference. It's going to generate a new state. So let me create that also. BA. Okay, right? By the way, not only this. Okay, particles can be in second and third where they can be interchanged. Okay, particles can be in first and third, they can be interchanged. Okay, now you see, okay, how many possibilities are there? Let me call R 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 ways I can put these particles together. So three states are there. So 3 memory locations. I have to put 2 entities like A and B into 3 memory locations. In how many ways I can put? Just a 3 to the power of 2, 9. 9 states, 9 arrangements possible. Let me say 9 arrangements possible. Okay, very good. So as per the Max Boltzmann, this is the story. Okay. Okay, let me draw a neat line. Now, Fermi-Dirac statistics. As per the Fermi-Dirac, what is this? Particles are indistinguishable. Indistinguishable means I can't distinguish them whether A and B. Both appear to me like a A. Okay, that is one implication. And one more is single particle in a state. Single particle in a given state. Okay, right? So now let's see the implications. What are the possibilities? Yes, 1, 2, 3. Now I don't see A and B separate. Both particles in state 1 and 2. They can't be in the same state for sure. Or they can be in second or third, but they can be in first or third. Only three states possible. Let me call this is arrangement 1, arrangement 2, arrangement 3. So three arrangements are possible as per the Fermi-Dirac. Now, what about Bose-Einstein statistics? In the case of Bose-Einstein, what they said is, for sure, particles are indistinguishable. Means I can't distinguish them. But the thing is, any number of particles can be in any state. Okay, right? So I have only two particles, so I will take them, both the particles in same state. Okay, any number in any state. Okay, let me write down now and plot the possibilities. S is equal to 1, 2, 3. Now the indistinguishability is there. Both the particles in state 1, both the particles in state 2, both the particles in state 3. So that is a possibility of putting all the particles in one state. But there is also chance, one more possibility is one particle in one state, another particle in another state. What is that? Two particles. One is in 1, another one is 2. One is in 2 and another is 3. One is in 1, another one is in 3. So the arrangements, let me give the names for the arrangement, are equal to 1, 2, 3, are equal to 4, are equal to 5, are equal to 6. Okay. So there are 6 possible arrangements as per the Bose-Einstein statistics. Remember, the Bose-Einstein statistics are Fermi-Dirac statistics or Max-Boltzmann statistics. They are the labels or the theory given for the natural existence of the particles. Okay. So I am just saying from the mathematical perspective to the mathematics side. Please don't think in that way that this statistics dictates the system. No, like that, nothing like that. The nature dictates, and for the dictated nature existence, we have given this kind of a labeling, this kind of a statistical distribution formation, mathematical formation. That's all. Now, looking at all the three cases, okay, just take all the three cases. Now, if you carefully look at, okay, let me take some kind of a comparison. What comparison I take? Let me define a variable xi, which is PR, the probability of two particles, okay, exist in same state, in particles in same, divided by probability of particles, two particles. In this case, two particles are there. That's why I'm writing two particles in different state. Okay. Right now, this is a xi. Like for example, let's find out xi for Fermi-Dirac statistics. How many particles are there in the same state? Two particles are there in the same state. Any available arrangement? No, 0. Right? Individually, there are 3. So this ratio is 0 for Fermi-Dirac statistics. What about this ratio for, okay, Bose-Einstein, BES? Now, if you see how many are there together, there are 3 arrangements, 3. How many are there separate? 3. It is equal to 1. Okay, so this xi is 1 for, okay, for Bose-Einstein. Now, what about xi for Max-Boltzmann? Okay, for Max-Boltzmann, if you see, how many particles are there together? How many arrangements? There are 3 arrangements. Okay, how many are there individually? There are 6 individually. Okay, so out of 9, 3 are together. Out of 9, 6 together. Okay, so if you want, you can put 3 by 9. 6 by 9, which is simply 3 by 6, which is 1 by 2. Okay, so this is a 50%. This is 100%. Okay, this is 0%. What is this conveying, this factor or this label or this parameter is? It is conveying chance of particles bunching together. Okay, right? See, for example, in the case of bosons, electrons, I see more chance, 100% chance they can bunch together. That is what happens in the case of, okay, a coherent light source. In the case of the single photon sources, which are called in coherent light source, we see a very good bunching of particles together. In conventional light source also, we see a bunching of photons together, because there is 100% chance of they can exist in the same state, exist in the same location. So that is what this Fermi-Dirac statistics from the outside, Bose-Einstein statistics from outside, MB statistics from outside, we can see things. Okay, right? So what do we do now? We quickly, okay, maybe I can conclude in 2 minutes time, and then we can take a break. Okay, so as per the MBS, Max Boltzmann statistics, let's say these two particles, the particle A in state 1, particle B, in particle B in state J. Okay, when so I can be 1 2 3, J can be 1 2 3 as per our scenario. So there is 3 into 3, 9 possibilities. Okay, right? Now interchanging the particles, okay, interchanging generates new state. Obvious, understood. Okay, when it comes to Bose-Einstein statistics, what is happening is, okay, now talk about location of the particle or their coordinates psi I, psi j, q, b. Now, what I am saying, particles are indistinguishable. Any number in any location. What do? I simply say both the particles are in same location. Sorry, just a minute. Both are in same location, psi I. Now, that is 3 possibilities are there, 3. And now, let's say there are 2 different locations, psi I, QA, psi j, QB. They can be interchangeable, psi I, QB, psi j, QA. Because by interchanging, I am going to get a new state. Okay, so this is a possible quantum state for Bose-Einstein statistics. These are like symmetric quantum states. In both the cases, if we see interchanging, the overall quantum state is not going to change. How many of them are there? There are 3 types. The first one is 3 types, and second one is 3 types. Okay, but in the case of, this is the Bose-Einstein statistics. In the case of Fermi-Dirac statistics, what is happening is particles are distinguishable. Okay, and particles are indistinguishable. Now interchanging the particles are going to induce a negative sign for the quantum state. So what are the quantum states? Could be just like here, quantum state psi QA, quantum state psi j QB, minus quantum state psi a QB, psi j QA. So these are the easiest way to represent a anti-symmetric quantum state. Anti-symmetric quantum state. Okay, fine. So Max Boltzmann, Fermi-Dirac, Bose-Einstein. In all the three cases, I know how to represent a quantum state representation and the quantum state eigen or a wave function representation. One is going to be a generic quantum state. Another one is going to be symmetric quantum state. The last one is going to be antisymmetric quantum state. Okay. So looking at the particles and finding their spin, you can just write down their quantum wave function. Okay, so we'll just quickly take a 5 minutes break and we are going to discuss further what we can derive in terms of, okay, in terms of partition function and all those things in the next. Okay, yeah, let's take a break, everyone. Yeah, welcome back everyone. Yeah, I see a very interesting question, very good question though. If the particles are indistinguishable, okay, and now in that scenario, if you exchange, does not, don't we think it should not yield a new does not yield a new state? Is it correct? Okay. Now the question is, what kind of particles they are? Okay. If it is the particles are spin integer, they have a spin, then I have a trouble. I can't generalize. If the particle's spin is integer spin, okay, example, bosons are photons. If you interchange them, they are going to generate a new quantum state which is similar to the old quantum state. So it is called symmetric quantum state. Symmetric quantum state. Okay, the systems evolve into new quantum state, but it's symmetric. The properties, overall properties may not change, but the arrangement got changed. So the changing the particles, their location is have some implication, but may not be on overall scale, may not, you will not see a great change in the quantumness. Okay, right? That's why you see a bunch of photons all in same state. The photons are interchanged in the location, doesn't make any difference. Okay, but when it comes to half integer spins, okay, which are fermions, example, electrons. So we always, starting from our school level, we start hearing electrons. I can't have same more number of electrons in a given orbit. I can't have same spin electrons in a given orbit. So the spins has to be always opposite. So in that way, they should be paired. Then only I can have two electrons in the same orbit. So the electrons, the spin coordinates are different. Okay, one is up spin, another one is down spin. So which means when I interchange them, it is going to affect the overall quantum state, but not by magnitude. The length of the quantum state remains the same, but it acquires a parity, negative parity. So it's called anti-symmetric state. Remember? Okay. Still, in both the cases, looking at individual particles from the very zoom out scenario, electrons are electrons. I see electrons have positive, negative charge. That's all. That's what I see. But if I go in detail, one electron probably spinning about itself in a clockwise manner. Let's say there is an electron, if you just take electron, if it is rotating in anti-clockwise, it is going to have a spin down magnetic momentum. Its angular momentum is downwards. Okay, so if you curl the finger towards its magnetic moment, it's a rotation direction, the thumb should show a magnetic moment, the angular momentum. Since the electrons are negative in nature, so you should simply take the opposite sign. So your finger should curl opposite to the rotation. Now it's a spin down. If the electrons are rotating in a clockwise direction, so now the curling finger is opposite to the rotation. The magnetic moment shows upwards. So the magnetic spin would be upwards. Angular momentum would be upwards and the spin would be upwards. Okay. So in the looking the way they are actually having spin or not, we should bother deciding whether their quantum nature is described by quantum state symmetric or quantum state being anti-symmetric. Okay, right? Now let's talk in terms of understand in terms of statistical physics. Okay, in terms of statistical physics terminology, which is, what are the statistical physics terminology is partition function. Okay, remember let's recollect, or instead of remembering, partition function is something which tells me what are the various possible ways I can arrange the given set of atoms into the different orders. We just saw in the previous case two electrons, two atoms, sorry, two particles arranged in three different ways based on Max Boltzmann, based on Fermi-Dirac, based on Bose-Einstein. Okay, so the partition function would list down various possible rearrangements, each arrangement giving us some energy ER, where ER stands for total energy of the system when it is arranged in an arrangement represented by R. Okay, how many R such R's possible? There may be many R's possible. So there are many such R's are possible. Okay, so in a previous very early case, here if you say Max Boltzmann case, how many R's are possible? 9 R arrangements are possible. In the Fermi-Dirac, there are 3. In the case of Bose-Einstein, there are 6 arrangements. So the partition function is going to put them all together and giving us some interpretation. Okay, right? Now, what would be the total? How do I calculate the total energy? Depending on the scenario, I would calculate this energy. For example, let's say I have how many number of particles? Let's say I have n number of particles. N particles are there. Okay, and there are ways I can arrange. For example, let's say R runs from 1 to how should I say? R runs from 1 to okay. Let's say any infinite. Okay, right? I will not truncate at some point. Right now, let's say I want to write down what is the energy overall for a particular arrangement. Let's say I want to write a particular arrangement total energy. Okay. Now, if you see, there is n1 particle out of capital N exists in a state where the energy of the state is E1. So one particle exists in that state, it will correspond to one E1 energy. How many particles are there? N1 particles are there. The overall energy coming from that particular state is N into E1. Simply what I mean, let's say there is a ground state, there is an excited state, and so on, second excited state and so on. The energy for the ground state is E0, energy for the excited state is epsilon 1, epsilon 2, and so on. Let's say there is one particle is there, total energy is 1 into E1. If there are two particles are there in the state, so 2 into E0. Okay, so likewise, so there are N2 particles in E2 with energy E2, and so on. I can go in increasing order. Okay, now this is a total energy of the particle. How many number of particles are there here? The sum over N R, okay, is equal to capital N. That is must, because overall particles which I have chosen is fixed. Okay, now if I have to write down a partition function for this scenario, how do I write down? The partition function is summation over all arrangements. Okay, R is equal to 1, R equal to 2, small r I am talking about, and all of them set together, I'll have capital R exponential minus beta. Beta is a Boltzmann constant multiplied by ER. This is the partition function. Now, what is this partition function is useful? We'll just see to find out, okay, the mean number of particles in a given state. Yes. Okay. Now, power of partition function, we'll see power of partition function. Okay, right? Okay, so what it does, it helps me to calculate the mean number of particles in a given state. Yes, okay, helpful to for finding mean number, average number, mean number of particles in a given state. Yes. How many number of particles are existing in a state? Yes. If somebody asks, so what you should do? I should find average R is equal to S, average value. Okay. So in the quantum mechanics, it is also stored expectation value of N R equal to S. Okay. Now, if I know the partition function, as per the Gibbs principle, the average number of particles in a given state, yes, or a mean number is simply, okay, let me write, yes, overall is equal to, you take the partition function in the denominator, the Gibbs principle, as per the Gibbs principle. In the numerator also you write a Gibbs principle, partition function. Only difference you are going to do, inside a summation you are going to put ns. Okay, right? Okay, wait a minute. Right, this is a Gibbs principle as per Gibbs principle. Okay, now the question is how to find this fraction of two summations. Okay, explicitly if you want, you can write down them as summation over R ns exponential of beta into, we just derived what is the ER is, okay, what is this ER? ER is E1 R1 plus E2 R2 and so on up to any number. I'm not going in terms of arrangement. Okay, this is the numerator. What is the denominator? Denominator is also same thing. Only difference is I don't have ns in the denominator. Okay. Now what do I do? Denominator is a partition function by the way. Okay. Now if you carefully look at it, in the numerator, okay, I have this ns factor extra. Can I do one thing? What I will be doing is, let me take a derivative of partition function with respect to, what is that? With respect to energy of that orbit, where the orbit arrangement is in such a way, the number of particles in that arrangement is ns. Okay, what I mean is, there is an orbit with energy S, the number of particles in this orbit is ns. Okay, right? So we just have that earlier. So I have taken n equal to 1. Let's say how many particles are there in n equal to 1 means n1 is 3 particles. Okay, so that is what. So in general, there is ns of particles in an orbit, okay, with the energy Es. Okay, so that energy I take the differentiation of the Z partition function with that energy. Okay, now inside a partition function, where is that energy located? Summation over R, E beta, E1 R1, E2 R2, and so on. Es, okay, Es. I'm writing in terms of es. Okay, let me write down. Okay, in terms of I was writing in terms of n1s, right? N1, N2. Okay, so I should not write in terms of R1, N1, N2, N1, N2, and so on. Okay, N1, N2, Ns, and so on, anything. Okay, now if I differentiate dz with the Es, okay, so what do I have is, okay, so let me take the separately, that particular element, E beta Es Ns multiplied by E beta E1 N1 E2 N2, except this term, everything is there. Okay, Es minus 1, Ns minus 1. Next term is Es plus 1, Ns plus 1, and so on. Okay, now you are taking a differentiation. You are taking a differentiation of this entire thing with respect to Es. By the way, this is independent of Es. Independent of Es. This is dependent of Es. Dependent on Es. So only the first element will be differentiated. What do I get? Differentiation of exponential minus beta Es Ns with the, okay, Es is minus beta Ns exponential minus beta Es Ns. Okay, so that is what I'm getting. Very good. So the dz Es, sorry, dou z by dou Es is equal to, now, beta Ns. Let me put inside the summation to be on safe side. Okay, exponential minus, now this factor is not changed, I can put it inside, so I'll say beta into Er. Okay, which is minus beta Ns. Okay, some Ns would be always inside, beta can come inside because Ns may dependent on arrangement. Ns exponential minus beta Er. Very good. So the derivative with respect to z, what I am getting? I am getting this factor. So let's say the summation over R Ns E beta Er is, okay, 1 by beta minus, okay, 1 by beta minus dou z by dou Es. Okay, so I just derived what is the numerator of this Gibbs principle. Okay, so see, the numerator of Gibbs principle has Ns with a partition function in the inside of partition function, which looks like derivative of the partition function with the some particular energy, which means the average number is, or a mean number of Ns is minus 1 by beta dou z by dou Es divided by z. Now, if you carefully look at this fraction again, I can play one more trick. What is the trick? Yes, if you just consider derivative of dou Es log of z. If you take it, what do you get? Log of any function, log z, log of z is 1 over z derivative of z Es. Okay, right? So dou z by dou Es by z is this log function. So Ns, or the mean number, is equal to, okay, 1 by beta derivative of Es with the log of z. Okay, so this is the easiest way you can find the mean number. If I know the partition function, you take the partition function derivative with respect to the energy, with the energy I want to like how many number of particles on an average would be found in a given energy. Yes, if you want to find, you just find the partition function, take a derivative of the partition function with that energy, boom, you will get the total average energy. And only thing you have to add a factor minus 1 by beta to find the mean number. Okay, so no need to do anything else. If you know the arrangement of the particle in terms of partition function, from there you can get the mean number. It is that simple. Okay, right? Now let's recollect. As per the Max-Boltzmann statistics, as per the Bose-Einstein statistics, also called as photon statistics, as per the Fermi-Dirac statistics. Three cases. Now I have total number of particles are, let's say, fixed. Okay, right? As per the Maxwell-Boltzmann statistics says, given nr could be taking values 0, 1, 2, 3, and so on. What I mean, in a given state, there will be no particles, or one particle, or a two particle, or any number of particles. Okay. What about Bose-Einstein? Bose-Einstein case, remember, indistinguishable. Okay, it is enough to specify indistinguishability. Okay, and one more thing is any number of particles can be in any given state. So the arrangement is n1, n2, and any number. Okay, remember total should sum to n, but any number of particles could be in one state, but indistinguishable rearrangement is not going to make any difference here. Okay, right? So the lowest possible energy in this Bose-Einstein case is, let's say there is a n0 is the lowest possible energy, ground state energy. All the particles say, okay, I'm sorry, let's take ground state energy. All the particles can exist in the same ground state. Okay, right? Okay, so in that case, what is the total E low possible, which is simply n number of particles, all particles. Here I have total n particles, all are existing with energy E0. So this is the lowest energy possible as per the Bose-Einstein statistics. Okay, but as per the Fermi-Dirac statistics, okay, what it means, the nr value would be 0 or 1. That's all. In a given state, how many particles can exist? Either 0 or 1. The total number of particles is anyway fixed here. Okay. Now here the arrangement is n1, n2, and so on up to some n. Remember here n1 is 0 or 1, n2 is 0 or 1. That's all. Okay. Now what is the lowest energy possible for this arrangement? There may be one particle with a 0 energy, lowest energy, one particle. The next energy is one more particle. Next energy is one more particle. So lowest energies possibles are the sum of all energies. Okay, let's say this is low Fermi-Dirac. Now you see the Fermi-Dirac low energy, okay, always greater than low energy of Bose-Einstein. Okay, remember. So much lower, because in Bose-Einstein statistics, I can pick a lowest energy and stack all the particles in that lowest energy. Photon has a particles inside a cavity of volume V. Okay, but in the case of Fermi-Dirac, for example, electrons, I want to arrange them in an atom. I can't arrange them as everybody in ground state. No, I have to go s orbital only 2, p orbital some number, d orbital 5, and so on. I can only stack the electrons as per that. Okay. Now, okay, a generic mean number if I want to calculate. Right? So I can play the same trick what I played with the partition function. Okay, what the partition function I played there is, I first try to calculate what is the mean number. Inside calculation, I just saw there is a nice trend between the partition function in the denominator and a rearranged partition function in the numerator. So from there, I derived what is the mean. So now I want to know, if I have a photons, how many number of photons can exist with the energy Es on an average. Okay. So what I want, special case. Okay. It's called photon mean number. I have, let's say, a bunch of photons. Okay. So all the photons can be arranged in different ways. So if they are arranged, if there is an energy state Es, how many number of photon particles are there in that energy state Es? The question is, if there are n particles, okay, by the way, photons, and they're allowed to arrange, okay, right? If they're arranged, then what is the average number of okay, particles exist in given state of energy Es. Okay. Now I want to find what is the average energy in a given state. Okay. I'm sorry. Either I put a bar, I put a rectangle, a right angle and rectangle around the Ns. Okay. So as per the Gibbs principle, what is this quantity? Its quantity is all the various Ns arrangements. Ns. Okay. I would, okay, exponential minus beta, right? Es, sorry, how should I write? Okay, wait a minute. En, okay. How many number of particles are there in the particular state? Okay, Pen, I think it's fine. Yeah. How many number of particles are there in that nth state? Na? Okay, n. So n is equal to 1 particle with energy E1. Okay, that's good. So n exponential minus beta En into n. Okay, so n is a subscript and n also gets multiplied. You are confusing with the n, so what you do, you just put a subscript. Yeah, right? Fine. This is as per the partition function. Now, if you see in the denominator, I have partition function. In the numerator, I have partition function, which is slightly rearranged. So what I'll do, I'll just show this as minus b1 over beta derivative with the es, we did this earlier, log of the partition function. What is the log of partition function? Summation over ns exponential minus beta en ns. Okay, right? So now just concentrate on the log of this factor. Okay, so log of ens exponential minus beta en ns. Okay, now look at inside, which is appear to be a minus beta in whole ns. Okay, so now run the ns values from 0 to any number which is ns stands for 0, I'll get 1. ns stands for 1, I'll get exponential beta e1. Okay, exponential minus beta e2, exponential beta, and so on. Okay, right? So wait a minute, which is going to be equal to, right? This is something like summation over x to the power of n, which is going to be, if x value is less than or close to 1, I'll have 1 minus 1 by 1 minus x. So looking at this exponential, you can conclude it is actually a series of summation. Okay, so this is equal to 1 by 1 minus exponential minus beta. Okay, so in general, I should write x. So my x is e. Yeah. Okay, so 1 by 1 minus exponential beta s, which is going to be e exponential beta en divided by 1 exponential beta en minus 1. Okay, right? Now, so yeah, that's true, right? Now I have to find the log of this factor, log of this exponential minus beta n divided by exponential beta n minus 1. Okay, so what is this? Would be, okay, so if you just take a derivative of this thing with respect to es and multiply it by 1 by beta and minus sign, what you would be getting is simply you would be getting 1 by exponential beta es minus 1. That's all. Because when you take a log with these things, derivative, and then you will get rid of everything and only left with this. This is called photon statistics. Okay, this is also called Planck's distribution. Planck's distribution. And also, okay, right? So this is a boson. So this is a boson statistics or photon statistics or photon distribution or Planck's distribution and so on. Now we want to do Fermi-Dirac distribution, that we will do tomorrow. Okay. So in the Fermi-Dirac distribution, we can derive the mean number by using that. Okay. So let's say somebody wants to know, right? How should I find the partition function for classical scenario? Okay. Just for completeness, the Max-Boltzmann statistics. Okay, I want to write partition function here. Okay, even though it's a classical scenario, still we can have a partition function. Now let's take n particles. By the way, they are distinguishable as per this. So n1 particles could be in one state, n2 particles in one state, and so on. The summation over all nr is n, capital N. Okay. Now, if nr particles are there in one state or in rth state, okay, by rearranging, we would be getting a new state because a distinguishable new state. Okay, how many number of states are possible with nr rearranging? So there are nr factorial number of arrangements, okay, arrangements are possible with NR particles. Okay. Now the question is, total number of particles are n capital N. So therefore the number of possible arrangements for all the particles, all the n particles, which would be simply total n factorial divided by, within that there is n1 particles in one state, so their factorial, n2 factorial, and so on. Okay, so this is a total arrangement, several arrangements. So this is actually capital R, which we are referring. Okay, right? So the partition function would be such factorial arrangements with the exponential minus beta, energy in each state, sorry, like energy of certain E1 energy, how many number of particles are there? E2 energy, how many number of particles are there? Okay, so beta into total energy, right? So this is a total energy. Okay, so now the partition function is summation over n1, n2, and so on. Okay, n factorial, n1 factorial, n2 factorial, and so on, exponential minus beta, e1, n1, e2, n2, and so on. So this would give the grand partition function, right? Okay, right? So this is a classical case. This is called grand partition function. Okay, right? So specifically, what is this arrangement R is given here. So each R would look like this. How many such R's are there? This many number of R's are there. So these are number of or types of arrangements. Okay, right? So now explicitly, if I want to find out what is the Z would look like, Z is equal to, okay, n factorial is not going to depend on, capital N is not going to depend on summation. What you can do, send it out. You can just individually, you can put each summations, exponential minus beta e1, n1 divided by n factorial, summation over n2, exponential minus beta e2, n2 divided by n2 factorial, and so on. So basically this is simply equal to, okay, some multiplication of exponential minus beta e1, exponential minus beta e2, exponential so on overall n. Okay, so this is there is an alternate method to calculate what is this value. I have given in the notes. You please check that. Okay, so this is a Max Boltzmann statistics based partition function. Okay, so there are a couple of questions. I'll quickly take those questions. Okay. Okay. Yeah, okay, at 420, I guess, angular momentum denoted by L, but magnetic momentum is denoted by M or mu. Both are in opposite direction for the electrons. Yeah, right. So angular momentum is literally, okay, angular momentum is literally R cross P. Okay, and magnetic moment mu is calculated from, okay, the way the way it is rotating. For example, nucleus, around the nucleus, if the electron is rotating, okay, so if the electron is negative charge, if it's going like this, anti-clockwise, the corresponding current is DC current is clockwise. So magnetic momentum is calculated as, for the electron, remember, I into pi r square, current into area or the perimeter which encircles the electron motion. So magnetic moment pi r square is a magnetic moment. Okay. And what is the direction? Direction is, you take the current direction. You take the current direction as your fingers and show the magnetic moment downwards. Okay. So for a current magnetic moment, which would be inwards, sorry, inwards is a cross symbol. Okay. Magnetic momentum is inwards and angular momentum is outwards. Okay, this is the reason. Because of the charges, electron charges opposite, and we always refer the like, even though electrons are the working horses in current carrying, but we always refer in terms of positive charges carrying the energy. Okay, so the current is always referred to positive charge. Even the amount of charge stored in a capacitor is referred in terms of positive charge accumulated on the positive plate, not on the negative plate. Same charge of opposite parity is accumulated on the negative charge plate. We will not refer to that. That is how it is being referred. Okay, right. And R means possible number of accessible states. Yes, you are absolutely right, Lakshmi ji. Or see, the best example is our case. We had easiest to remember. Okay, small r taking 1, 2, 3, 4, 5, 6, 7 means the capital R is arrangement of r taking 1, r taking 2, and so on, r taking n. So overall together, bunch together. So my capital R is 1, 2, 3, and 9. That is a overall arrangement, the way it is arranged. Okay. Okay, then yeah, bosons. Right, for today we did it for bosonic distribution or photon statistics. Tomorrow we will do using Fermi-Dirac statistics, mean number calculation. It is slightly tricky, so we'll concentrate on that tomorrow. Okay, so for today's notes, I'll definitely upload to the drive. So our canvas, you please refer it and you can understand. If there is any doubt, you can come back tomorrow. Fine. I'll stop at this point. I'll hand it over to the Academy. Arka sir.
So thank you, sir. Thank you for a very informative session that we had. I think we are going to continue this tomorrow also, and we'll conclude. Obviously, our course is concluding tomorrow. And participants, please, if you have any, please go through the material today and by tomorrow morning. And if you have any further questions, we can. I think we can take it tomorrow when we begin the session. If you have any other questions.
Arka sir, I'm sorry to interrupt. There is a one question
Yes,
I missed there. Qubits are which type of particles? Please explain. Okay. So qubits are, like say I'm in general talking about, qubits are the ones which allow me to create superposition states of two classical bits, 0 and 1. So these qubits can be fall into any category. If they're falling into the bosons, the qubits are realized out of photons. If qubits are falling into the fermions, so in that case, the qubits are realized out of electrons. Okay, so these are the two cases which we are discussing here, but there are other ways of realizing qubits. For example, NV center in the diamond, it's a dipole. Inside a dipole, NV center can exist in multiple quantum states. That is altogether a different zone of existence of qubits. Right now, whatever we are talking, the qubits being exist as an electron are fermions. Qubits exist as a bosons or photons. Is there any relationship between quantum computing and neuromorphic computing? Yeah, neuromorphic computing is something inspired from neurophysics, I guess. So, yeah, I have no straight away answer to comment on this. Definitely, there is a difference. Okay, right? Yeah. So, using neurons, there is applied quantum computing algorithms have been designed. So those are like quantum-based neural networks. Okay, so yeah, it is just upgraded versions of conventional neural networks. So neuromorphic computing probably a slightly different version of it. I'll check and I'll let you know tomorrow. Okay, thank you. Okay, so that's it for today. We'll meet tomorrow.
Thank you, sir. Thank you very much. And we'll meet again tomorrow at 3 o'clock. Tomorrow will be obviously the last session, as we all know. So anyway, thank you, sir, once again. By the way, participants, I would want to remind you about quiz 2 once again. You know that we have opened it for one more time, and the closing time of that would be tomorrow evening, tomorrow night. So what we want to say is